Okay, chemistry time. This is already going to go great, I can tell. At least this time I remember to do picture-in-picture. It is picture-in-picture now, isn't it? Okay. Chemistry time. Today we're talking about, let's just call it measurements in science. Measurements in, let's actually specify measurements in chemistry. In case you aren't aware, chemistry is the name of this class, and you're here, so I hope you're aware. The objective is determine the role of measurements in chemistry. Determine the role, R-O-L-E, not R-O-L-L, that's a different thing. The role of measurements in chemistry is like what they do. The role of measurements in chemistry, R-O-L-L, would be like if you went to Daylight Donuts and got a donut and that donut was named the role of measurements in chemistry. And it was like a magical object that if you ate it, you would know about measurements in chemistry, which actually I wish existed because then you guys would just know. I could just feed you the donut and then you would know it. However, that does not exist. And so we're today going to talk about the role of measurements in chemistry. So probably the first thing that comes to mind when we think about chemistry measurements is the kind of measurements, the type of measurements we use are not really the ones that we're used to using in our daily life in the United States of America in 2025. In the United States of America in 2025, we use things like, how tall is Lucas? You tell me. 6'3", Lucas says, referring to 6 foot 3 inches, which he isn't. I mean, I could very easily provide videographic evidence, but we won't to protect his identity. He's not, though. But 6 foot 3 inches is a unit we're used to measuring. And then we could also say, how much does Lucas weigh?
682 pounds.
Lucas is in my 600-pound life. Lucas is just hitting the hot pocket so hard. No, how much honestly do you think Lucas weighs? All muscle, 190, all muscle. 194 of all muscle. But 194 referring to what unit is implied there? Pounds, which is an American, we call it an English or an imperial unit. But the units that we use in chemistry are those within the SI, which is, this will make it even more complicated for you. This is in French, the système, I think the accents go like that, internationale, you don't say the E in French, international, d'unités. Yeah. Lucas won't. It's basically against Lucas's religion to write things that have accent marks over them, so he's not going to do that. But just so you know, in English, this is to be translated the international system of units. The reason I even put it in French is that way you know that the SI, first of all, you should know that not everything is about America, but the SI stands for International System. The reason it's what you would call the wrong way around, because that's how Americans are used to seeing everything, as if it's different, it's wrong. The reason you would say it's the wrong way around is because it comes from a different language that you know nothing about. Do you know French, Ami? Okay, that y'all know nothing about. So it's the International System of Units. We often, at least in America, we often call this the metric system. And that's not, in the strictest sense, that's not true. The metric system has a different meaning, and it's really the SI is like the modern or the more modern version of the metric system, which was reworked in the 70s, 1960. And this system is made of 7 base units. Well, let's try to listen. What are the most basic units of measurement? We're going to say what their name is, give their symbol, and then we're going to write what they use to measure, what physical quantity they use to measure. What are the most basic universal quantities? That is, quantities about physical observable reality that we can measure. That was not a yes or no question. There are 7 of them. What are the most basic quantities that we measure? That's not I see what you're getting at. That would be a unit. What does that measure? What quantity does that measure? There you go. Distance or length. So distance or length is measured by, in the international system, not kilometers, but can anyone think what the base unit might be? Meters. Abbreviated lowercase m measures distance or length. Okay? What other basic quantities could we measure? Nope, weight is not one of them. Mass is one of them. Mass. And in the international system, what do we use to measure mass, do you think? Kilograms is exactly right. Now someone, I wish, would have the perspicacity to say, but how come kilograms is the base unit when kilometers wasn't? It's just because kilograms are generally considered more useful because they're larger. I kind of wish it was grams personally, but they didn't ask me. I wasn't even alive. I was negative 31 years old when this was made. So kilograms is the base unit of mass. What other basic fundamental aspects of nature could we measure? Again, distance and length. Nope, volume is not. Because you remember, even the equation for volume says that it's length times width times height. Those length, width, and height are all measured in meters. That's more basic. So nope, density is mass divided by volume. So, there's not just these things. Just length and weight are the only things. Just because Lucas is 6'3" and 194 of pure muscle, these are the only two kinds of measurements that matter. No, that's not true. What else? There's another one we use even. There's another one we use in your daily life more often than these. Time. There you go. Time. What's the base unit of time, do you think? Seconds. The other ones, well, there's one more that you probably should get, and the other ones will be kind of a struggle for you. No, you should get it. That's a good hint. What are the basic measurements do we measure in the laboratory or even out in the wild? This one really matters to you when you're outside. Light. Temperature. But hey, you hold on to that one. Ethan said a good one, but don't do it yet. I'm going to capitalize temperature because we usually use capital T for temperature, and that's measured in capital K, which is kelvins. Now this is the same scale as degrees Celsius, but Kelvin is a more basic unit, and so I'll put kelvins up there. Again, it's the same scale as degrees Celsius. So you could, and you might see, and in fact your book might have, nope, it has kelvins. Some books might have degrees Celsius as the temperature. It's the same scale, it's just that Kelvin starts at absolute zero, so there are no negative numbers, and degrees Celsius starts at zero as the boiling point, or sorry, the freezing point of water. What's the one you said? Light. We call it in science luminous intensity, like how strong the light is. Like think about, for instance, if I, just in my dream job, exactly this except I have a spotlight right here, the luminous intensity would be much greater. Because right now the light's coming through the window a little bit, but it's the afternoon and those windows face east, and so it's not really coming in. And it's filtering in through these purple curtains that I have over my LED lights, and so it's not really doing it. But if I had a really good spotlight here, like a badminton spotlight. What? Batman spotlight, yeah. The spotlight of badminton. Luminous intensity is measured in, the abbreviation is lowercase c, lowercase d, and it's called candelas, like candles. It's sometimes called standard candles. Candelas, like the word candle with an AS. Candle AS. This next one is very important in chemistry. Eliana's heard of it before. How do we measure the amount of matter? Which is different from mass. Mass, no. Eliana, how do we measure the amount of a substance in chemistry? Nope. Sometimes, but that's not the most basic way. Not the mass, the amount. Just how many atoms there are. Or how many molecules there are. Mole. Yep, mole. Which the unit is mole, M-O-L-E, like the spot on your chin that you got to shave around, or the little animal that burrows in the ground. And the abbreviation is M-O-L. So that's actually not a very good abbreviation. Abbreviated from 4 letters to 3 letters. And then the final one is important really to Lucas when he works for his dad. What do you think is the most basic unit of that? No, but that is a good guess. You're on the right track. Even better guess, but that's not it either. Yep, amperes. Amperes, abbreviated capital A, which measure electric current. It's supposed to be. It's supposed to be an A. Ethan, little pest. Oh, there I go. Yes, thank you for your advice on handwriting, Ethan. You of all people. So those are the most basic units. They're called the base units, and then we can derive them through the process of derivation. They become derived. So some derived units are, well, everything else, but some of them that we use so far this year are milliliters, which are equal to 1/1000th of a liter, which is equal to 1 cubic decimeter. So decimeter is a tenth of a meter. That's equal to a liter. That's equal to a liter. A thousandth of a liter is equal to a milliliter. What other units have we used so far this year? Well, you remember that we did grams per milliliter, right? That was density. Well, gram is a derivation. Have you heard the word derived before? Yes. Derived means like it comes from. So gram is derived from, it comes from the base unit for mass, which is kilogram. So that unit, gram, is already derived, but we divide it by another derived unit, milliliters, to get the, it's supposed to be. We divide by milliliters to get another derived unit. So anytime we've done math or attached a prefix, which is just another way of doing math, to one of these, or many of these, we get a derived unit. The prefixes we commonly use are, well, why don't you tell me?
Kilo.
Let's start with the bottom. I'll tell you some of them, okay? Let's start at the bottom. 1/1,000,000th. Lowercase p, pico. So a picometer is 1/1,000,000th of a meter. A picogram is 1/1,000,000th of a gram. A picosecond is 1/1,000,000th of a second, etc. You know how prefixes work, right? That's the way it is. 1/1,000,000th is nano, which is lowercase n. You might have heard of a nanometer or a nanosecond. I should have drawn this table first before it's going to look really scratchy here in the middle. Oh, I think I've done it wrong. Forgive me. This should be trillionth. This one should be billionth. And then micro is millionth. Just add 3 zeros to it. Are you serious? There's no way that's true. Just add 3 zeros to them. The Greek letter mu, which is like a kind of fancy M with a long tail, is micro. And then 1/1000th is milli.
Micro, is that one?
Yep. What? What? Centi is 1/100th. Yeah, because I started from the bottom, which I've actually, the dozens of times I've taught this, I've never started from the bottom. It's actually kind of foiling my plans too. 1/10th is, as I said before, lowercase d is deci. Then we have the base unit. I'm out of room too. I'm going to start erasing things above it, which I can do because I have a whiteboard, sorry. Going up, we don't use this one very much, but 10 times the amount is capital D, which is deca.
What is that word? The M one? Yes.
Micro?
Yeah,
that. Oops, sorry, I wrote the wrong thing. 100 is capital H, which is hecta. We don't use that one very much either. Then we have kilo, which we do use a lot. And then we have mega, capital M, which is one, oh, what am I doing here? Kilo, and then I wrote kilo again. 1,000 is kilo. 1,000,000 is mega. And then 1 billion is giga. Capital G is giga. And then 1 trillion, and that's where we're going to stop because I run out of room, is capital T, and it's tera. Like, nope, not like that. This started out pretty neat, actually, I will have you know, but then it got a little bit, kind of how I do everything, actually, though. Thanks, Lucas. So those are, one way we derive them is by adding prefixes. Other way we derive them is just by doing math, like grams per milliliter, grams per mole, meters per second. Those are derived units because they have math done to them. And not all those examples were per, but there are other ones too, like square meters, right? Meters squared, meters times meter. Or a Newton is a kilogram meter per second squared. So that's lots of units smooshed together. So all the other units that we use in science are based on these units and their prefixes. Now, we talked about unit conversions, dimensional analysis. We talked about density. If you're watching this video in the future and you want to learn more about either of those things, you can refer to my video I made either yesterday or the day before on physical science, or there are lots of other ones. Just search up dimensional analysis. Other sources are available. If you want to watch someone good do it, just type in dimensional analysis and watch Sal Khan or someone who actually knows what they're talking about do it. But there is one more thing I want to talk about before we're done with this, and that is these two, where will I do it? Just up here in the corner. These two targets. They're targets. And they have to do with data grouping and I'm trying to say it without saying the word. Truth, maybe? If something is precise, that means that all of the measurements that usually we refer to this as tools, all of the measurements will be to the same value. So if something is precise, if you pretend these are targets and you're shooting them with a, I don't know, what do you shoot? Darts, if you're doing darts at the bar, or you're shooting at the shooting range, or you're firing arrows during archery and PE class, and they all land here, you fire 5 shots, and they land like that, this is considered precise. They're tightly grouped, is how we would refer to that in target practice. And in data, that would show up as if we took 5 readings, we might get 16.30, 16.29, 16.31, 16.30 again, and 16.32. They're all tightly grouped. Whether that's right or not, we don't know. This then is accuracy. Accuracy is how close to the truth it is. So accuracy is how close to any accepted value it is. And so the precision of a number, when you take a measurement in science, you understand this is an analogy. The precision of a number is how closely your own readings compare to each other. Or maybe how closely your individual readings compare with hers and hers, right? That would be precision. But how close it is to the truth is a different matter, and that's accuracy. So if I draw them, if we do it like this, is that accurate or precise or neither or both?
Neither.
That's neither accurate, or I would say neither. Thank you, Lucas, for correcting my English. Neither accurate nor precise. We already talked about it can be precise anywhere. Like even if I'm firing off over here, aiming here but hitting there, that's still precise. They're still tightly grouped. It's just not accurate. Well, what we want in the laboratory, ideally, we calibrate the instruments so that they are more accurate, and then we buy expensive, nice instruments so that they are precise. Like the centigram balance that costs $700, that's precise because it can measure things to the nearest hundredth of a gram. Centigram. It's accurate because I calibrate it so that 1 gram is actually a gram in truth, but it's precise because of the quality of the equipment. So what we really want in chemistry is to be both accurate and precise, right? Get near the target, near the center of the target, the correct value almost every time. And this is also why, if we are measuring the volume of a liquid, we want to use the smallest graduated cylinder that will actually fit it, because the smaller the graduated cylinder, the more precise the measurement can be. It's also why we want to use that instead of a beaker. The beaker only has graduations of 100, 200, for instance, and so we don't really know what's in between those. But when we use a graduated cylinder, we have the graduations. Do you have questions about accuracy and precision? Do you have questions about the International System of Units? Not right now, not yet. Do you have questions about dimensional analysis that we did that was supposed to be a review? I call them unit conversions. Your book calls them dimensional analysis. Both are true. You will have questions about that as we go over it, as we talk about your worksheet. Oh, and significant figures is the other thing that's in your text. We did that during our lab. Do you have questions about significant figures? I think in previous years, I have included the discussion of the significant figures in this video, so if you want to watch me talk about it, you can go back to other years and watch that one. It's probably even in the title. But do you feel like you have a pretty good grasp of significant figures as it is? Two places you can look are your book, which you'll have to do some for the chapter review also, and those other videos I was talking about. Bye.